Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 8. Householder Method. Finding the eigenvalues of dense matrices is very expensive due to several factors, including high computational complexity, numerical instability, and memory constraints. These unfavorable factors require the use of optimized algorithms and specialized techniques to make the process more efficient, especially for large-scale applications. Alternatively, to overcome adverse effects, the eigenvalues of a dense matrix can be determined much more efficiently by reducing it to a tridiagonal matrix through a series of similarity transformations. In this regard, the objective of the householder method is to transform a symmetric matrix into a symmetric tridiagonal matrix having identical eigenpairs. Once a matrix is transformed into the tridiagonal form using the householder method, the matrix becomes available for use with a more efficient eigenvalue computation method, such as the QR algorithm. The method using orthogonal transformations has become a key tool in numerical linear algebra because it avoids some of the complications of direct methods for large systems. To be able to employ the method, the matrix A is assumed to be a well-conditioned symmetric matrix and has n eigenvalues with n linearly independent eigenvectors. The orthogonal transformations are sequentially applied to zero out the pertinent row and column elements all at once, except for the tridiagonal elements. The elements that are zeroed out in prior steps are not altered in the subsequent operations, unlike the Jacobi method. This algorithm requires n-2 orthogonal transformations, expressed as illustrated below. He matrix P sub k is the transformation matrix at the kth step, defined as given, and it is called the householder matrix, which is symmetric and orthogonal, and the vector v is a unit vector. The householder matrix can be constructed as follows, where u is a direction vector and its dot product is the magnitude squared. We construct the vector u, whose first m-1 elements is 0, that is, explicitly shown as. We define the transformations as the transformed matrix A sub m is partially tridiagonal up to row m. The householder matrix P sub m has the identity matrix up to row m. The objective of this transformation is to obtain the vector u such that it is normalized to vector v. Setting u equals x plus s times e1, where s equals plus or minus magnitude of x, we find, where x is the lower m-1 elements of the first column of the householder matrix, and e1 is defined as the unit vector. Of course, in the first step, the scalar d is computed as follows. We can now construct the elements of the vector u at mth column as follows. The transformation procedure is illustrated in this figure. The householder matrix P1 is constructed, and the matrix A1 is set to matrix A. The householder matrix is operated on A1 to give the transformed matrix A2. Then, the current householder matrix is operated on A2, which leads to the transformed matrix A3, and so on. This process is continued until the transformed matrix becomes a tridiagonal matrix. The orthogonal matrix P is embedded in the resulting tridiagonal matrix T, where delta ij is the Kronecker delta, i.e., delta II equals 1 and delta ij equals 0 if I is not equal to j. Note that the first m rows and m columns remain unaffected by the similarity transformations. Additionally, we can restrict the calculations to the elements in the upper triangle of the matrix A sub m since the transformation preserves the symmetry. The advantages of the method are: the householder method is fast, accurate, and CPU time efficient. It always works for any non-singular symmetric matrix. It systematically zeroes out elements without explicitly performing division, which minimizes round-off errors. It is stable and does not require pivoting. It works well for large-scale problems where stability is a priority. The disadvantages of the method are: the method is bandwidth-intensive heavy, diagonally dense, and not parallelizable. It requires operations in the order of cubic power of matrix size, compared to the modified Gram-Schmidt method, which can be faster than the householder method in some cases. Every reflection modifies the matrices P and A. Let us consider the following positive definite and symmetric matrix. We will use the householder's method to transform it into a tridiagonal matrix. To eliminate the entries below the subdiagonal in a column, we will apply a reflection transformation. We start with the first column of the matrix with a goal to eliminate all values below the first subdiagonal element while keeping the structure of the matrix intact. Instead of directly modifying the matrix, we create a special vector that helps in transforming the column. The quantities S and D, required for the construction of the householder matrix, are computed as follows. The vector U, i.e., the householder vector, is designed in such a way that when applied to the matrix, it zeroes out the unwanted elements while preserving numerical stability. As it is applied to the original matrix, the product of U and its transpose becomes. Now that we have D and UU transpose evaluated, we can construct the householder matrix, which leads to having found the householder matrix P1, we can apply it to perform the transformation on matrix A1, which gives the matrix A2. Notice that the resulting matrix has zeros in the desired locations of the first row and first column. Next, using the matrix A1, we will repeat the same process on the submatrix, constructing a new householder matrix for the second column. We start with the second column and compute the quantities S and D as follows. The length of the householder vector U decreases by 1, which leads to the product matrix UU transpose is found as follows. Using the currently found D and UU transpose, the householder matrix P2 is found. With the matrix P2 at hand, we apply it on matrix A2 to obtain the matrix A3. This transformation created zeros at the desired locations of the second row and second column, as well as below the third row and beyond the third column. The matrix A3 is now in tridiagonal form. As we have seen, the method reduced a full symmetric matrix into a symmetric tridiagonal matrix, which will be processed later on to calculate the eigenvalues. The eigenvalues are presented below. See video 9 of this chapter to find out how eigenvalues of tridiagonal systems are obtained. With this note, we end this lecture. That is all for now. See you next time with another topic. Bye.